The thermal history of the Earth is the study of the cooling history of Earth's interior. It is a subfield of geophysics. Thermal histories are also computed for the internal cooling of other planetary and stellar bodies. The study of the thermal evolution of Earth's interior is uncertain and controversial in all aspects, from the interpretation of petrologic observations used to infer the temperature of the interior, to the fluid dynamics responsible for heat loss, to material properties that determine the efficiency of heat transport. Overview. Observations that can be used to infer the temperature of Earth's interior range from the oldest rocks on Earth to modern seismic images of the inner core size. Ancient volcanic rocks can be associated with the depth and temperature of melting through their geochemical composition. Using this technique and some geological inferences about the conditions under which the rock is preserved, the temperature of the mantle can be inferred. The mantle itself is fully convective, so that the temperature in the mantle is basically constant with depth outside the top and bottom thermal boundary layers. This is not quite true because the temperature in any convective body under pressure must increase along an adiabat. But the adiabatic temperature gradient is usually much smaller than the temperature jumps at the boundaries. Therefore, the mantle is usually associated with a singular potential temperature that refers to the mid-mantle temperature extrapolated along the adiabat to the surface. The potential temperature of the mantle is estimated to be about 1350 C today. There is an analogous potential temperature of the core, but since there are no samples from the core, its present-day temperature relies on extrapolating the temperature along an adiabat from the inner core boundary, where the ion solidus is somewhat constrained. Thermodynamics. The simplest mathematical formulation of the thermal history of Earth's interior involves the time evolution of the mid-mantle and mid-core temperatures. To derive these equations, one must first write the energy balance for the mantle and the core separately. They are Q surf equals Q sec man plus Q rad plus Q cmb. Display style Q underscore text surf equals Q underscore text sec man plus Q underscore text rad plus Q underscore text cmb for the mantle, and Q cmb equals Q sec core plus Q L plus Q G. Display style Q underscore text cmb equals Q underscore text sec core plus Q underscore text L plus Q underscore text G for the core. Q surf display style Q underscore text surf is the surface heat flow W at the surface of the Earth, and mantle Q sec man equals M man C man D T man slash D T. Display style Q underscore text sec man equals M underscore text man C underscore text man DT underscore text man DT is the secular cooling heat from the mantle, and M man display style M underscore text man C man display style C underscore text man and T man display style T underscore text man are the mass, specific heat, and temperature of the mantle. Q rad display style Q underscore text rad is the radiogenic heat production in the mantle, and Q cmb display style Q underscore text cmb is the heat flow from the core mantle boundary. Q sec core equals M core C core D T core slash D T display style Q underscore text sec core equals m underscore text core c underscore text core dt underscore text core dt is the secular cooling heat from the core, and q l display style q underscore text l and q g display style q underscore text g are the latent and gravitational heat flow from the inner core boundary due to the solidification of iron. Solving for d t man slash d t display style dt underscore text man dt and d t core slash d t display style dt underscore text core dt gives d t man d t equals 3 minus q surf minus q cmb 4 pi rho m c m r 3 minus r c 3 plus q rad v m rho m c m display style frac dt underscore text man dt equals frac 3 q underscore text surf q underscore text cmb 4 pi rho underscore text m c underscore text m r caret 3 r underscore text c caret 3 plus frac q underscore text rad v underscore text m rho underscore text m c underscore text m and d t core d t equals q cmb a c l plus e g r I r c 2 rho I d r I d t cmb eta c minus r c 3 minus r I 3 3 r c 3 rho c c minus 1 display style frac dt underscore text core dt equals q underscore text cmb left a underscore text c l plus e underscore g left frac r underscore I r underscore text c right caret 2 rho underscore I frac doctor underscore I dt underscore text cmb eta underscore text c frac r underscore text c caret 3 r underscore I caret 3 3 r underscore text c caret 3 rho underscore text c c underscore text c right caret -1. Thermal catastrophe. In 1862, Lord Kelvin calculated the age of the Earth by assuming that Earth had formed as a completely molten object, and determined the amount of time it would take for the near surface to cool to its present temperature. Since uniformitarianism required a much older Earth, there was a contradiction. Eventually, the additional heat sources within the Earth were discovered, allowing for a much older age. This section is about a similar paradox in current geology, called the thermal catastrophe. The thermal catastrophe of the Earth can be demonstrated by solving the above equations for the evolution of the mantle with q cmb equals 0. Display style q underscore text cmb equals 0. The catastrophe is defined as when the mean mantle temperature T man display style T underscore text man exceeds the mantle solidus so that the entire mantle melts, using the geochemically preferred Urey ratio of U R equals 1/3. Display style Urey equals 1/3, and the geodynamically preferred cooling exponent of beta equals 1/3. Display style text beta equals 1/3. the mantle temperature reaches the mantle solidus, i.e., a catastrophe, in 1 to 2 Ga. This result is clearly unacceptable because geologic evidence for a solid mantle exists as far back as 4 Ga, and possibly further. Hence, the thermal catastrophe problem is the foremost paradox in the thermal history of the Earth. New core paradox. The new core paradox posits that the new upward revisions to the empirically measured thermal conductivity of iron at the pressure and temperature conditions of Earth's core imply that the dynamo is thermally stratified at present, driven solely by compositional convection associated with the solidification of the inner core. However, widespread paleomagnetic evidence for a geodynamo older than the likely age of the inner core, approximately 1 Ga, creates a paradox as to what powered the geodynamo prior to inner core nucleation. Recently it has been proposed that a higher core cooling rate and lower mantle cooling rate can resolve the paradox in part. However, the paradox remains unresolved. 2 additional constraints have been recently proposed. Numerical simulations of the material properties of high-pressure temperature iron claim an upper limit of 105 W per meter K to the thermal conductivity. This downward revision to the conductivity partially alleviates the issues of the new core paradox by lowering the adiabatic core heat flow required to keep the core thermally convective. Also, recent geochemical experiments have led to the proposal that radiogenic heat in the core is larger than previously thought. This revision, if true, would also alleviate issues with the core heat budget by providing an additional energy source. Back in time. See also Earth's magnetic field. Earth. Further reading.